This video is intended to teach you about molecular shapes. Now, when we say molecular shapes, that seems pretty self-explanatory. It's the shape of molecules. But there's a lot that goes into it, but I'd like to first put into context the why. Shapes are really important, not only in chemistry, but chemistry is part of anatomy and physiology. When we humans smell things, it's the particles of whatever we're smelling going up through our nose and hitting these receptor neurons. These receptor neurons are unique to specific molecules. You have tens of thousands of them, which means that you're capable of identifying tens of thousands of different odors. And imagine, for the sake of simplicity, that this one receptor neuron here is for sugar. And so you go to your local bakery and you smell all the amazing cakes and breads, all are made with sugar. What's happening when you go into that bakery is that this sugar molecule is actually airborne. Even though the bread isn't floating around in all of its individual molecules, some portion of those molecules that make up bread are airborne, which is why we can smell them. So that sugar molecule heads right up your nose, and let's say it hits that one receptor for sugar. The way that it does that is through a lock and key mechanism, meaning that we have receptors for individual molecules, meaning that if any other molecule passes by this one receptor that's meant for sugar, it's not going to latch on. Your brain is not going to be able to say, ooh, that's sugar. Well, because it's not. If you think about the analogy of a lock and a key, the lock in this case is the receptor neuron, and the key is sugar. Anything other than sugar is not going to bind to that specific receptor neuron for sugar. If you think of some other common smells that you enjoy, maybe lavender, roses, pizza. Pizza is actually a combination of several different odors. You've got the crust, you've got the cheese, you've got the toppings that each hit different neurons inside your nose and send some signals to your brain and make your brain say, ooh, that's pizza. But this sugar molecule is really big, and so to start understanding molecular shape from the basic level, these are some of the common molecular shapes. In fact, these are all that you're going to see in this class this year. We have linear, a couple different types of linear molecules: trigonal planar, bent, tetrahedral, trigonal pyramidal, trigonal bipyramidal, and octahedral. And we'll dive into those a little bit more on the next slide. So each of these shape names comes from a couple of different things. First, these shapes are relative to what we call the central atom in a molecule. And in these examples, the central atom is red. As you can see here, what's around that red central atom in all of these different shapes changes from shape to shape. And so these names are derived from two major pieces of information. One is called the electron domain geometry, and there are three types of electron domain geometry. The first one is linear, and what that means is that there are one or two pairs of electrons around the central atom. And notice the language specifies pairs of electrons. And those pairs of electrons could be either bonds to another atom or lone pairs of non-bonding electrons. And just to give you some context, in these models here, those green spheres are used to indicate pairs of non-bonding electrons. Meaning, say if we look at this trigonal pyramidal shape here, we can see that it has 3 bonds to other atoms, from the central atom, and then one non-bonding pair of electrons up top there. The second type of electron domain geometry is trigonal planar. And let's define trigonal planar as 3 pairs of electrons around the central atom. And I'm going to add a big number 1 up here to represent electron domain geometry. To determine the shape of a molecule, like we said, there are 2 parts. One is electron domain geometry, and then from the electron domain geometry, we can determine molecular geometry. So there's 2 pieces of it. Let's just remind ourselves that this is just the first part of figuring out what shape a molecule has. So the last type of electron domain geometry is called tetrahedral. And let's define that as 4 pairs of electrons around the central atom. A couple of examples of tetrahedral molecules in molecular shapes. We've got the bent shape here. We can see there's 1, 2, 3, 4 pairs of electrons. In this case, there's 2 bonds to other atoms and 2 non-bonding pairs of electrons for a total of 4 pairs of electrons. And down here for tetrahedral, we have 4 bonds to other atoms around the central atom. So what I'd like you to do is to think about electron domain geometry first when trying to determine molecular geometry. And so remember, we have 3 types of electron domain geometry. We have linear, trigonal planar, and tetrahedral. And remember, those describe the number of electron pairs around the central atom in a molecule. And for molecules with linear electron domain geometry, there's only one possibility for molecular shape, and that is also linear. And an example for that is hydrogen chloride or hydrochloric acid. And the second example for this is carbon dioxide. If we think about a linear molecule, or any molecule with just 2 atoms in it, the only possible molecular geometry for that is linear. Another example here that we already talked about is carbon dioxide, and if we look around that central atom, the electron domains are only going in 2 directions. And so this bond angle here is 180 degrees, making the molecule linear. Now moving on to the trigonal planar electron domain geometry, there are 2 types of molecular geometry within trigonal planar. The first is trigonal planar. And trigonal planar is best described as a central atom bonded to 3 other atoms. And I drew an example of this trigonal planar molecular geometry in a specific way. I drew it so that each of these pairs of electrons between boron and fluorine are as far apart from each other as possible. And that's something we'll get to in the next slide. The second example of trigonal planar electron domain geometry is the bent geometry. And we're still talking about 3 pairs of electrons around the central atom, but in the case of the bent trigonal planar geometry, one of those pairs is non-bonding, like in this sulfur dioxide molecule here. Notice there are 1, 2, 3 domains of electrons around the central atom. The result in that is a bent trigonal planar geometry. The last category of molecular geometry falls under the tetrahedral electron domain geometry. And the first molecular geometry I'd like you to know is the tetrahedral molecular geometry. And an example of that is methane. And in methane, and what really defines this tetrahedral molecular geometry, is that the 4 things around the central atom are all bonds to other atoms. The second type of tetrahedral electron domain geometry is called trigonal pyramidal. And the best and most common example of that is the ammonia molecule. Notice how there are still 4 things around this central nitrogen atom, making it a tetrahedral electron domain geometry, but 3 of those electron domains are bonding domains and 1 is a non-bonding domain, making its shape just a little bit different than tetrahedral, like in the methane molecule. And the reason behind that is that this non-bonding pair of electrons actually takes up more space than the electrons in a bond to another atom. And so it will give it a different shape. The last type of molecular geometry that I'm asking you guys to learn this year is called bent tetrahedral geometry. And the best example of that, and maybe the best example in science at all, is the water molecule. Notice around the water molecule there are 4 things. There are 4 electron domains, 1, 2, 3, 4, making it tetrahedral in terms of its electron domain geometry, but it's different from the other molecular geometries within the tetrahedral category because it's got 2 non-bonding pairs of electrons and 2 bonds to other atoms. I had mentioned earlier that each of these electron pairs, whether they're bonding or non-bonding, tries to get as far away as possible from other non-bonding or bonding pairs of electrons. Well, that's because they're both negatively charged, right? These electrons that are either in bonds with other atoms or non-bonding are negatively charged, and like charges repel each other. So no matter how many of these electron pairs are around the central atom, they're going to repel each other as much as possible. And one of the ways to quantify that repulsion is in the bond angle between the central atom and the 2 of the atoms around that central atom. And so let's go down this list, molecular geometry, one molecular geometry at a time, and assign some bond angles. The linear geometry is 180 degrees between the central atom and the other atoms in the molecule. If you think about it, there are 2 domains of electrons. The arrangement that gets them as far away from each other as possible is to put them 180 degrees away from each other. In the trigonal planar molecular geometry, there are 3 electron pairs around the central atom, and in the trigonal planar example, the bond angle is 120 degrees. And one of the nuanced facts about molecular geometry is that when one of those bonding pairs of electrons in this molecule is replaced with a non-bonding pair of electrons, the bond angle changes just slightly. Depending on what source you look at, you'll find that they call the bond angle of this bent trigonal planar molecule close to 120. Well, what does close mean? 119, 118, any of those numbers are fine. But what matters is that it's just a little bit less than 120 degrees. And why? Well, this non-bonding pair of electrons actually takes up more space and repels these bonding pairs of electrons a little bit more than a bonding pair does. Moving on to the tetrahedral molecular geometries. In the example of methane over here, the bond angle is 109.5. Now, in 2 dimensions, it looks like 90 degrees, but I'm going to ask you to use your imagination here in imagining this molecule in 3 dimensions. I'll update the drawing a little bit to reflect that. And if you look at this updated drawing, these bonds are meant to kind of show 3 dimensions in 2 dimensions by saying that this solid bond here is actually coming out of the screen and pointing toward you, while this this bond as represented here, is actually poking back through the screen in the other direction, making the angles just a little bit bigger than 90 degrees, about 20 degrees larger, but again achieving as much separation as is possible with this arrangement. Moving down to the trigonal pyramidal bond angles, with this lone pair above the nitrogen, even though there are 4 electron domains around the nitrogen, and we said that the tetrahedral was 109.5 degrees, what I'd like you to learn is that the bond angle here is just a little bit less than 109.5. Why? Again, that non-bonding pair of electrons pushes down and repulses the other bonding pairs of electrons just a little bit more. If you want to ascribe a number to it, some places you'll see 104.5, some places you'll see 107.5, depending on the molecule, but what matters is that it's just a little bit less than 109.5. And last but not least, the bent tetrahedral geometry. Because there are 2 non-bonding electron pairs, the bond angle is going to be less than 109.5, just a teeny tiny bit smaller than that in the trigonal pyramidal geometry, but again we'll just say less than 109.5 if you want to ascribe a number to that. If the trigonal pyramidal geometry was 107.5, let's call this bent tetrahedral 104.5. Again, just a really teeny tiny difference, but there is a difference. And what I'd like you to take away from this discussion about bond angle is that the number of electron pairs and whether the electron pairs are bonding or non-bonding has an influence on the molecular shape and the bond angle. The more stuff around the central atom in general, the smaller the bond angle is. Notice in the linear, where there's only 2 domains of electrons, we have our largest bond angle, and down here, when we have 4 things around the central atom, the bond angle is its smallest.